Hi, and welcome back. We are going to talk about section 10.5 today, which is going over rationalizing denominators with square roots. Now, you may have looked at some problems already, and you see something where it's like 3 divided by the square root of 7. And you're like, oh man, what does that mean? I'm seeing roots and fractions, and it's all crazy. It's actually super easy. So check this out. The process of rationalizing a denominator is simply clearing out any kind of radical value. If you're dealing with a monomial term like this, it's super easy. You multiply by the square root of 7 to both numerator and denominator. Why, you might ask? Well, I'm multiplying technically by something over itself, so I'm not changing the problem at all. But what I'm doing is I'm saying for the denominator, square root of 7 times square root of 7 is the square root of 49. Square root of 49 is 7. I am clearing that rational or that radical value from my rational expression. So I am clearing that radical value from the denominator. The numerator, simplify as you can. That just comes out to 3 radical 7 here, just like so. And that is it. That is all you get for rationalizing your denominator. Let's try another one. Say I have negative 6 over a square root of 12. In this case, you could technically simplify that square root of 12, but let's say we don't. Let's say we just go for it. So I'm going to rationalize with that square root of 12. Again, multiply top and bottom. That's going to be a negative 6 square root of 12 on the numerator. We'll come back to it. Down here, you have the square root of 144, which is the same thing as 12. That was the whole point. So anytime you're looking at a radical times itself like this, square root times square root, you're getting rid of that square root on purpose, and you're left with the radicand value. Now, let's talk about that square root of 12. We have a little simplification to do there. Technically, that's negative 6 times 12 is broken into 4 times 3. So you can pull this 4 out. Negative 6 times 2, square root of 3. Oop, that is a 12 on the bottom. Negative 6 times 2 is negative 12, square root of 3, over 12. And guess what? The 12s can cancel. That leaves you negative square root of 3. So don't drop that negative sign when you get to the final result. Okay, let's try another one. Let's say I have a fraction that is contained inside of a radical. So my entire radicand is a fraction. What I'm going to do is I'm going to see if I can simplify that fraction at all. I can't. So I'm going to split it up. I have the square root of 18, square root of 5y. I want to rationalize my denominator, so I'm going to multiply by the square root of 5y to both numerator and denominator. I know my denominator is going to be 5y. That's the whole point. My numerator, I have to do a little work. So 5 times 18 is actually 90. So I have the square root of 90, and that is y. Now that 90 technically could be broken down into 9 times 10y. That 9 could be pulled out, so that's 3 square root of 10y over 5y. And that is it. That is all you've got. So rationalizing the denominator, especially with a monomial term, meaning just a single radical, I keep saying rational, but a single radical in the denominator, single radical term like that, is pretty simple. Now, what if you get a binomial? What if you get something like this next problem, where you have 5 over 4 minus the square root of 3? Well, here's the problem. If you try to multiply by the square root of 3 to both top and bottom and call it a day, the problem that you're running into is, yeah, you'll clear the radical here, but you introduce a radical here. And that's a problem because you're still dealing with a radical in the denominator. So instead, what you want to do is multiply using a conjugate. And what is a conjugate? It's the same exact terms with the opposite operation. So I'm going to multiply by 4 plus the square root of 3 to both top and bottom. And here's why. We'll come back to the top, so I'm just going to write it up here. The denominator here, once we multiply, that's 4 times 4 is 16. 4 times this radical 3 is positive 4 radical 3. This is negative 4 radical 3. This is negative square root of 9. These middle terms cancel. Square root of 9 is a perfect square, so you can take that out. That's 16 minus 3, which is 13. That is your denominator value. So that's why you work with that conjugate value. It clears all of those radicals from your denominator. Now, coming back to the numerator, go ahead and distribute. That's going to be 20 plus 5 square root of 3. Nothing you can do there, so just carry it to the end result right here. And there you go. So that process also is not too bad. You just have to be very careful in determining what your conjugate is. So let's try another. I have the square root of 2 minus the square root of 3 over the square root of 5 plus the square root of 3. The question that I have is, what conjugate would I use? Well, I'm wanting to rationalize the denominator, so I'm not worried about the top. So yes, you have radicals everywhere, but I'm only looking at that denominator right now. So I'm going to use the square root of 5, square root of 3, and I am currently adding, I need my conjugate to be the opposite, so I am subtracting. What I do to the bottom, do to the top. So let's work one part at a time. I know my conjugates are going to clear that middle term, so I'm going to skip multiplying all the way out. You absolutely can. But what this is going to give me is the square root of 25 minus the square root of 9. Again, those middle terms would have canceled out. That is also going to be the same as 5 minus 3, which is 2 as my end result for my denominator. Let's talk about that numerator. So I do have a binomial pair I'm multiplying. So I'm going to look at this and say my first terms, I have square root of 10. My outer terms, minus square root of 6. My inner terms, minus square root of 15. My last terms, plus square root of 9. The only thing that could simplify there is that square root of 9. So I'm going to just kind of skip over here and go to the end and give myself a little bit longer of a line because that's a little bit bigger than I thought it would be at working it out. So that's square root of 10 minus square root of 6 minus square root of 15 plus that square root of 9 simplified to 3. And that is it. There are no other like radicals there. So that's what you're left with. Let's try this last example. I have 3 over the square root of m minus the square root of p. My conjugate value would be the square root of m plus the square root of p. What I do to the bottom, I do to the top. I know the denominator here will come out to the square root of m squared minus the square root of p squared. The difference of squares, that's the whole purpose here, so I'm jumping to the definition, which is the same as m minus p. The numerator, I'm left with just distribution, and so I have 3 square roots of m plus 3 square roots of p. And that is it. So ladies and gents, rationalizing denominators is actually super easy. You just have to be very careful if you're dealing with a monomial term, so a single radical expression in the denominator. you can use a radical term, single radical term to clear that out. So a monomial term with a monomial term. If you're dealing with a binomial, such as these three examples, you have to use the conjugate value. And this will be very important as you start getting into the next section where we talk about complex numbers and imaginary values. But for now, that is it for section 10.5. I'll see you in section 10.7 in just a few minutes, or as soon as you click play.